Professor, I have a quick question.
Sure.
When should we expect to see grades in the gradebook on Canvas?
I'm going to be doing dry lab number 1 today. In fact, I'll be doing a little bit of an lab today, depending on how busy it is. So you should start seeing that pretty soon. Most people do fairly well in dry labs if you finish all the questions. So you should get a pretty solid start. And then as far as if you've turned in your lab waiver and your lab safety contract, you're going to automatically get points for that. So
okay, thank you so much.
That'll take like 5 minutes to do. Okay, so as a review, I wanted to go over the alcohols in terms of primary, secondary, and tertiary, because that is key on terms of reactions, because each classification of the alcohol reacts differently under oxidative and actually reductive conditions as well. So a primary alcohol is always on the end. That's the easy one. The difference between the secondary and tertiary one is whether there is a hydrogen present or not. So if you've got two groups here coming off of that carbon, other carbons, for example, or nitrogens or whatever, it's a tertiary alcohol. And this guy can't be oxidized, where this can be oxidized once, this can be oxidized twice. Twice because it has 2 hydrogens, once because it has 1 hydrogen. Okay, so get used to looking at, if you see an alcohol, look at it and see what kind it is. All right. Alcohols are very, very polar. It has to do with this oxygen here. That's what makes it polar. And the reason why it's polar is because the bonds are at an angle coming out of oxygen. So it ends up being kind of like a pointy arrow. And as I said numerous times over the course so far, nature likes symmetry. So it's a very unsymmetrical molecule. Unsymmetrical molecules tend to be polar, particularly if they have an oxygen in them. Okay, because of that, alcohols, all alcohols have a much higher boiling and melting point than things like alkanes, alkenes, and ethers. As far as reactions go, alcohols undergo lots of different kinds of dehydration, in other words, pulling off water. The first one we talked about last time was under high heat, 180 degrees C, and under oxidative or acidic conditions, a water molecule can be pulled off forming an alkene. Frequently, there is a mix. Frequently. If it's on the end, there's no mix. And sometimes cyclic alcohols will have no mix also. So simple cyclics, alcohol cyclics will have no mix. Usually you have a mix though. And that's because you can get that alcohol to degrade that water one of two ways, and that gives you the mixture. Okay. Under lower temperature conditions, an alcohol can then form up with another alcohol, forming an ether. So let's say these were different alcohols. What would happen is you would end up with a mix, and the predominant mixture would be a mix of, say this was a ethyl group, and this was a methyl group. You end up with a mix of ethyl and methyl on each side of the oxygen. In this class, the alcohols are going to be the same. So basically, where they would hook up, the two OHs would hook up together. And that would give you the combined ether. And of course, because it's a dehydration, it'd kick off water. If the two alcohols are the same alcohol, you're going to end up doubling the backbone. Now, under oxidative conditions, that's where the primary, secondary, tertiary comes in. And you'll end up forming either an aldehyde, ketone, or no reaction. The reason why you can get two oxidations out of a primary alcohol is because you've got two hydrogens that can be removed. The secondary alcohol only has one to be removed, so it can only be oxidized once. And then a tertiary alcohol has no hydrogens to remove, so it can't be oxidized at all. All right. So using this flow chart now, we've talked about a lot of reactions so far. Multi-step reactions are trickier than single-step reactions because you have an intermediate here. And the question is, what are they? How do you figure it? Okay, so on now we have an alkene here, and we have a ketone. So going to our chart here, there's a ketone. And to get a ketone, you've got to oxidize an alcohol, get the ketone. To get an alcohol, one of the ways to get an alcohol is with an alkene. So the intermediate step then is the alcohol. So we're going alcohol, oxidize the ketone. To get the alcohol, we add water. And an acid to the alkene, and we'll end up with the alcohol. And the alcohol will then go further oxidation down to the ketone. That's what we're going to do here. So the intermediate now is an alcohol. All right, so let me review again how we got that. There's the ketone. We're going to go backwards now. Okay, the ketone has to be oxidized. And it's going to come from a secondary alcohol. So this alcohol here has to be a secondary alcohol to give you a ketone. Then to make a secondary alcohol, it's going to come from a alkene. Okay, so usually in our class, except for ethers, and there's another class in Unit 2 we're going to talk about. But as far as Unit 1 goes, basically the reactions are going to all have the same backbone. So the backbone we're talking about here is 5 sided cyclic group. And what we're going to be doing is we're going to be making an alcohol from the alkene. And then we need water to do that. Under acidic conditions. That'll give us the alcohol. Now, normally you get a mix, except with cyclic, frequently, not all the time, but frequently you will not get a mix if you're starting with a cyclic alkene and hydrated. Once we have the secondary alcohol, now this is secondary alcohol now, remember, because that's the only way to get a ketone is oxidizing a secondary alcohol. So here's the step where we oxidize the secondary alcohol. The second step, the first step is we're hydrating an alkene to get the secondary alcohol. Again, this is secondary. Gotta be a secondary alcohol. If we put all of them together, this was what I was trying to do up here. In a nicer format, this is what it's going to look like down here. All right. You guys should have some questions about this. The most important tool you can use in figuring out reactions, I keep emphasizing it, is this chart. You're going to be able to flow through this chart backwards and forwards to get these reactions. No, I'm going to give you lab 2 today, handout like I did for lab 1. Because my lectures will follow what was in for lab number 2. Okay, Kaylee. So you don't have to bring your lab packet today. All right. No questions about this? And the extra worksheets I put on Canvas, one of them had some multi-step reactions in it. Last time someone asked me about some questions about the reactions on alcohols. Did we cover your question through this lecture today and last time? It was a guy. Okay. All right. And what I wanted to do is to, there's lots of different kinds of alcohols. As I mentioned last time, there's a horrendous amount of alcohols biologically, plants, animals, yeast, everything. It's a very important concept. Okay. And there are also multi-alcohols on the same backbone. So here we have a 2-carbon backbone. Here we have a 3-carbon backbone. Now you're going to see when we make soap, during the process, we're going to end up making glycerol, which is a 1, 2, 3 propa triol. When you take fat under alkaline conditions, you end up producing glycerol and soap. And one thing about aromatic alcohols is they act like weak acids. I had this discussion with an advanced instrument class, Dr. Atkins. She was putting together over the summer, and one of the issues was they had a chromatograph, a machine that produced a chromatograph of different kinds of alcohols, and one of them was phenol, and they didn't realize it was also a weak acid, which really affected how it behaved in relation to the other alcohols that were not aromatic. And they'd forgotten about that. Okay. There's two ways to name ethers using a oxy branch. So in this case, this would be the oxy branch. If it was one carbon, it would be a methoxy. The other way to name it would be a sec-butyl. That would be the sec-butyl there. This would be the ethyl ether. This is the official way to do it, though. This one here. Most people name it this way. Ethers can be cyclic as well. These two are very important ethers to get to know because these form furanoses, carbohydrate. These form a pyranose, carbohydrate. Okay, ethers, we talked about, they're not as polar as alcohols, so they're not as sticky as alcohols, so their boiling points are lower. Now, what we didn't talk about last time were because on the periodic table, sulfur is underneath oxygen, you can also get thiols, which is a alcohol only, instead of oxygen, it's using sulfur. These are also important biologically. Natural gas has no odor. And the problem with natural gas having no odor, if you have a gas leak, you can't smell it. You don't know the gas leak is there. Or unless you have a inferior nose like me that cannot smell natural gas when there's a leak. One of the things, excuse me, I'm developing a new lab with garlic. And it has to do with the characteristics of an enzyme that works on a chemical called allium. And that allium, when you cut the clove of garlic or onion, makes this compound called propane thiol. And that's what you smell, what makes you tear when you're cutting garlic and onions. You can turn off that enzyme with heat and low pH, and that's kind of what the lab is all about. Skunks, we all know skunks smell really bad. Well, that's to do with a thiol. Now, the only reaction you're going to need for thiols is oxidation. What happens is, remember, this is like an alcohol. So when you, under oxidative conditions, a thiol will combine together like this, kicking off water. Sort of like an ether, only an ether has one oxygen, this has got two sulfurs. And they connect together via the SH. So if we had something like this, so we have a 3-carbon backbone, 2-carbon backbone. When we oxidize these guys, now I'm going to flip this like this. Those two are going to combine together to give you that. In other words, the two S's hook up. Now, this is a particularly important reaction biochemically because there is an amino acid called cysteine, and its unique functional group is a thiol. So when you have two cysteines together, they hook up together and form this double sulfide bond. And that means those two amino acids are permanently hooked together. Now, if the amino acid is part of a protein, that protein now is going to be hooked together as a cross-link with those two cysteine amino acids. That's what makes hair curly or straight, is how the cysteines and the protein in your hair are configured. You can change that configuration by getting a perm. And what a perm does is it breaks this SS bond to two SH and SHs. Then we reform the hair, either straighten it or curl it, and then reform it again under oxidative conditions back to the SS bond. And that's why a perm is permanent, because we have a covalent cross-link in the protein. It's also why perms stink so much, because you have to reduce this, break the bonds, and we have to oxidize it to remake them. So this is an important one. Okay, let's see. Problem 8 on worksheet 7. Yes. Let me finish this part and I'll pull it up. Okay, so we're going to do reduction like this in this class. So oxidation is losing hydrogens, reduction is gaining hydrogens. One other reaction, which is really important biologically, is that thiols love heavy metals. This is why lead and mercury are particularly poisonous. It's because what happens is it binds up with cysteine, permanently. The only way to get rid of that metal is for you to excrete it by your protein being dissolved. Now, if this protein happens to be part of an amino acid, that amino acid, I mean, excuse me, part of a enzyme, that enzyme then will be deactivated because the heavy metal modifies the active site on the enzyme. Now, environmentally, we have problems. And back in the 70s, they eliminated leaded gasoline. Before that, whenever a car would burn gasoline with lead in it, it would spew out a form of organic lead called methyl lead. And that methyl lead was just spread all over the countryside. Well, guess what? That lead in the organic lead molecule would bind up with organisms, proteins, which could lead to enzymatic breakdowns. That's one of the big reasons they eliminated that unleaded. Now, that was a big fight. The oil industry has huge lobbyists, and it took a long time, but they finally got it through. And now, throughout history, we've had heavy metal spills. Japan had a big problem, caused a lot of birth defects. Up in Tacoma, there was a lead smelter right in Tacoma that used to spew out smoke when they would produce liquid lead from lead oxide or lead ore, and it polluted the countryside from all the way from Olympia all the way up to British Columbia, and it was considered an EPA Superfund site. So if you lived in a community near Tacoma or in Tacoma, the EPA would come in and remove the dirt from your yard and put new dirt on. It's part of the Superfund. It was one of the biggest ones in our country. It's really bad. It also polluted the sound because this heavy metal would obviously float to the bottom, and then fish would then eat bottom feeding fish. Would eat stuff on the bottom, then bigger fish would eat the bottom feeding fish. It was a big long chain. So there's signs around Tacoma Sound that says, do not eat the fish. They don't say why, but this is why. So this thiol binding with a heavy metal is a really important reaction. Okay. Polyfunctional compounds. We're not going to talk about these till we get into the carb chapter, but basically, this is what glucose looks like. It's both an aldehyde and an alcohol. And in fact, what happens is this aldehyde reacts with this alcohol and produces the cyclic glucose. Like frequently you see. And that's called a acetal. We're going to cover these in very much detail in the next chapter, not the next chapter, but the first chapter of Unit 2. Okay, and biological compounds have all kinds of functional groups all over them. That's what makes biochemistry sometimes very complex. Okay, so that is Caitlin, what reaction were you talking about?
If you went back to the thiol reactions, it's like for either of them, it's like 2R attached to an SH, right? But there's no like OH group. So I'm wondering
Right.
like just how it's an alcohol.
On the periodic table, you look at a periodic table. I'm going to find the periodic table here. Let me show you that. I'm going to find a periodic table there. Oh, here's one. Okay. Because sulfur is underneath oxygen, has the same chemical characteristics of oxygen. That's why act very similarly. That's why this is called a thiol, and this is an all, as far as the reaction naming goes. Was that your question?
Yeah, I'm wondering then how we would know like what's a thiol, what's a diol, if there's no indication of how many OH groups there are.
Well, there are no OH groups, there are SH groups.
Okay, so is anything with an SH group automatically a thiol?
If it sticks out like an OH group does, yes.
Okay. Are
So
there other ones we would need to know?
in other words, that's a thiol.
Mm-hmm.
That's a thiol.
Right. Are there other compounds like that that we would need to memorize?
Well, none so far. I'm trying to think if there are any. You mean that act like this because they're in the same group kind of deal?
Yeah, like if it had a CLH, is that like also a thiol or like no?
A COH?
No, a Cl, like right next to the S, a chlorine, chloride.
I'm not following you.
Like just okay, so now we know anything with an SH group that's sticking out is classified as a thiol. Are
Yes.
there any other elements or like branches that we need to memorize that would categorize something as a thiol, a diol, when there's not an OH group?
Yeah, but not so far. We're going to find
Okay,
we're going to find the whole series of nitrogen compounds that stick out like that.
okay, got it. Thank you.
Um, let's see.
No, it's okay. I don't want to overwhelm anyone.
No, I was just trying to think of probably the biggest one, and it's got a whole chapter. This is called an amine. There's a whole chapter on amines. Chapter 15 is amines. Um,
And those are on our amino acids, right?
yes.
Okay.
A single amino acid has an NH group. This is what an amino acid looks like. And there's something here that distinguishes the different amino acids. So that's the amino side. This is the acid side, hence the amino acid. In cysteine, as we talked about cysteine, looks like that. And there are 20 amino acids in our body. And there are 15, I believe, that are essential that we don't make. You know, there's glutamic acid, which is how they get MSG, and there's quite a few of them anyway. So, okay, so going back to this, let's call it an aside. The reason why the sulfur acts like the oxygen is because it's underneath, directly in the same group on the periodic table as oxygen.
Right, I'm good. Thank you.
Okay. So this is a big deal anyway, environmentally. Okay, all right, so let's see, what I want to do is okay, so it was worksheet number 7. Problem 8. Yes. Yeah. So you're going to take those SHs, stick them together. So what it's going to look like, let's see, this is a propyl, 2 propyl groups. So this is propyl thiol or propane thiol. So let me go over so I can write on. I can't write on this. So these are 3 carbons now. So 1, 2, 3. Oops, why not? I'm sorry. I was treating it like an ether. The way to do it would be to like that. This is probably the one that is easier to visualize. So did that answer your question?
Yes, how would we name it?
Don't worry about naming these guys. They're so rare that don't worry about naming them. These guys, the simple thiols, you can name because they're similar to alcohols. But when we start getting these thioethers, I mean, you name it dipropyl thioether. I mean, that would be the simple version. So it would be dipropyl thioether. But don't worry about that. And the main thing is just know that when the thiols are oxidized or biochemically oxidized, the S's hook up together. Now, if we had this, we would form, this is called a peroxide. And the reason why that would happen is because it's the same reason the sulfur happens under oxidative conditions. And by the way, that's one of the reasons why, another reason why oxidative conditions for humans or for biological systems are bad, because if we have a lot of alcohols, every stress this big time in our bodies, those would be all susceptible to forming peroxides. And if that happens to be part of an enzyme, that enzyme would become non-functional. Okay, so problem number 8 on that worksheet number 7. Is that okay?
Yes, thank you.
Okay. So the last chapter in our unit is aldehydes and ketones. Okay, a double bonded oxygen to carbon is called a carbonyl. We're going to have two kinds of molecules where the carbonyl group is used. With an aldehyde, which is on the end, and a ketone is in the middle. Acetone, you probably heard about acetone. That's probably the most common aldehyde, excuse me, a ketone. It's used in nail polish remover. It's used with around epoxy. It's frequently used as a solvent for non-polymerized epoxy. Formaldehyde is used a lot in the production of plywood. And that's one of the reasons why if you buy a brand new house in the state of California, on the plywood will be stamped, this causes cancer. And it's the formaldehyde that causes the cancer. So it's not a very nice molecule. And the reason why it's not very nice is because it's extremely reactive. So it gets in the middle of biochemical reactions, not good stuff. Naming aldehydes, take on the AL ending. So we have backbone of 4, functional group, going to be a ketone in this, excuse me, an aldehyde in this case. And then we've got some branching. So this would be 3-bromo-butanal. Now, the problem with when I write sometimes my A's and O's kind of merge. So whenever I do an alcohol and an aldehyde, I try to be really careful to make sure the O's and A's are distinguishable. Okay, another example. Remember now this was a common issue last week in the Wednesday lab, is determining the backbone. Now, some people would say this is the backbone here. That's not the backbone, because that does not contain a functional group. This is the functional group here. So the backbone has to contain the functional group. So it's either this way or this way. These are the same. In this case, we have an ethyl branch. Functional group is an aldehyde. So it's a 4-carbon aldehyde. So it would be a butanal, 2-ethyl butanal. And frequently, I like to put dashes in between each group, so it's real distinct what's going on.
I have a quick question.
Sure.
Hello. I have a question.
Yeah.
So on the first example, it says 3-bromo.
Yeah.
How is it 3-bromo? Wouldn't it be 2-bromo?
No. The backbone with the function group determines the numbering.
So why wouldn't you count H as 1? Because if that's the functional group, is the C.
Yeah. The backbone is a carbon backbone. H's don't count.
Okay. Got it. Thank you.
Now, with aldehydes, the aldehyde functional group is always carbon number 1.
Okay. Got it.
Can you number the other example too? Oh, you already did.
I'm sorry, what?
Never mind. I got it.
Did you ask me if I numbered the other one?
Yes.
As I was numbering it?
Yeah.
Okay. All right. And again, I want to really emphasize the backbone, except for alkanes, has to include the functional group. Now, I'm going to be adding some worksheets for aldehydes and ketones, because originally those worksheets only included my old unit 1, which didn't include aldehydes and ketones, just went up to alcohols. So I'm going to add 1 or 2 more worksheets. Again, we can work through those next on Wednesday. Okay, as far as ketones go, it's the same thing. We've got to find the longest chain that contains the functional group. So this is going to be a 5-membered backbone. That's a ketone. The was going to be ONE. So this would be 3-methyl 2-pentanone. We can also have cyclic ketones. This would be a cyclohexanone with a methyl group. Now, it depends on which way you number this. If you number this like this, it'd be 6-methyl cyclohexanone. 2-methyl cyclohexanone would be the preferred one. This is a solvent frequently. Another solvent. This is MEK or methyl ethyl ketone is used a lot in the paint industry. Also is acetone. Okay.
I have a question.
Sure.
How do we distinguish a ketone from an aldehyde if their functional group it's still O double bond C, right? They have the same.
The carbon that contains the carbonyl. So for an aldehyde, if I understand the question right, an aldehyde is going to be, so let's do like that. So your backbone is going to include this carbon there. Going to include this carbon. Is that your question?
Yeah, so in other words, like an aldehyde will be more of like carbonyl at the end versus a ketone, it would be within the backbone.
They're both in the backbone. Just because it's on the end.
Yes, they're both in the backbone, but I guess what I was trying to say, the ketone, it's more within like in the center, not the number one
Yeah,
carbon.
ketones, that's a good point. Okay, aldehydes are always one. Ketones are always not one. Because they've got to be in the middle. So they're going to be 2, 3, 4, whatever. They cannot be one. Okay.
Perfect, thank you. That explains it a lot.
Now, the problem is if you have two aldehyde groups in one molecule, then it gets complicated, but you don't have to worry about that here. Okay. The main thing is the aldehyde carbon is always on the end, and it always, no exceptions, always part of the backbone. And it always defines that as carbon number 1. With a ketone, because it's in the middle, it can never be 1. But it also has to be the carbon that the double bonded oxygen is attached to has to be among the carbons that are on the backbone. Okay, does that help?
Yes, a lot. Thank you.
Cool. All right. Physical properties. Okay, so aldehydes and ketones are kind of halfway between. Don't forget, down here we have alkenes also. And we have all alcohols are high. Now, you need to know this for this unit, where these lie. So, things that have the lowest boiling point have the least polar atoms and combinations in them. The ones that have the highest boiling points have the most polar atoms in it, mostly oxygen. Single bonded oxygens. Double bonded oxygens are less polar. Now we're going to get them to a combination of a single bonded carbon oxygen and a double bonded oxygen when we get to organic acids. And then those are going to be even more polar. So those are going to be up high up here. But know this relationship here. Okay. All right. Again, because of the oxygen, we've got polarity there. Hence, that's the reason why it can hydrogen bond with water and hence have a higher boiling point. The more polar the molecule, the more soluble it is in water. Okay. All right. We already talked about oxidizing a primary alcohol. It's oxidized twice because it has 2 hydrogens there. First oxidation forms the aldehyde. The second one forms the carboxylic acid. You could also call this an organic acid until we get to the chapter on carboxylic acids. A secondary alcohol, because it only has 1 hydrogen, it can only be oxidized once, hence it forms a ketone. And then because the ketone has no hydrogens here, it can't be oxidized any further. So it stops at a ketone. That's one test you can use to test if you think you have an alcohol, but not sure what kind of alcohol. You can oxidize it and then test your results. If you end up with an acid, you know you started with a primary alcohol. If you ended up with a ketone that's non-acidic, you know you have a secondary alcohol. If nothing happens, you know you have a tertiary alcohol. So in other words, under oxidative conditions, you throw an alcohol in there unknown. You form an acid, boom, you know it's primary. If you don't form an acid, but something happens, you know it's a ketone. In other words, the oxidizing agent would change color, something like that. Some way to know that oxidation reduction has happened, you know you have a ketone. If it's nothing happens, then you know you have a tertiary alcohol. We have an aldehyde oxidized to the acid. Okay, so this is the oxidizing agent here. And we have acetone here and benzaldehyde here. So when the oxidizing agent goes into the ketone, nothing happens because the oxidizing agent is still yellow. When the oxidizing agent goes into the aldehyde, it reacts with a changed color. Okay, you need to know this reaction. Tollens, basically a Tollens reagent will make an aldehyde turn the silver here. Let's let me do this here. Okay, Tollens agent basically is a silver cation, Ag plus. It reduces the Ag plus to Ag0, which is silver metal. So that's a reduction. Remember, with oxidation reduction, oxidation cannot occur without reduction at the same time. So when the aldehydes oxidize, it goes to the carboxylic acid, and because it's in a basic environment, it forms the salt. Okay, let me give you an example. Okay, so oxidation reduction, Tollens reagent. Now, they frequently use this also with carbohydrates, because carbohydrates are aldehydes and sometimes ketones. Okay, so let's do a simple aldehyde. in a basic environment. So remember, the silver is oxidized. Silver metal. And this, not oxidized, excuse me. This is oxidized. But normally would be oxidized to the acid, but because it's in a basic environment, you end up with the salt. So this becomes say this is sodium hydroxide. So the tests. The endpoint of the reaction is if you get a silver mirror, you have an aldehyde. Okay, now there's a similar reaction we're going to talk about as a Benedict's reaction. So we have two reactions, and what's going to happen is if we started with a ketone, there would be no reduction of the silver to silver metal. Okay. Another reaction, it's called Benedict's reaction. Same concept. It's an oxidation reduction reaction. Okay, so glucose, for as far as we're concerned now, is an aldehyde. In fact, it's called an aldose. So once we dump this Benedict solution, which is basically copper cation into, and this is really, they're both glucose. Just different concentration. They're both an aldehyde sugar, different concentrations. So we dump the copper into the aldehyde sugars, we get an oxidation reaction. So the copper, instead of nice blue, let's do this. Calling that red as being nice. It's kind of an orange, red, it's kind of a gunky looking stuff. Bottom line is that it definitely reacts because the blue definitely goes away. So bottom line again is, here we go. Basic reaction. So the aldehyde oxidizes, copper reduces. And there are two other test reactions. These are the two you need to know though. So before Collins and Benedict's. So if we were going to use the same, starting with Hokanau, And this is a very fast reaction. The silver is a much slower reaction, but this Benedict is really fast, within seconds. Okay, we need to know those two reactions. Don't worry about this. There are two exceptions to this reaction. That's what they're talking about there. Okay. Now, these are the reverse arrows that I talked about when I had the nice flow chart. In a reductive environment, instead of an oxidative environment, the aldehydes can go back to a primary alcohol, and ketones can go back to secondary alcohol. So here we have a 3-carbon backbone. This is a 3-carbon backbone alcohol, and because it's an aldehyde, we produce the primary alcohol. Similarly, 3-backbone ketone. So that primary, secondary, tertiary alcohol interplays all the time in these different functional groups. Okay. This reaction here is what makes carbohydrate chemistry. What happens when we get an alcohol and an aldehyde together, or a ketone and an alcohol together? We form an intermediate and then a final product. So I'm going to cover these extensively when we get to Unit 2 carbs. So we're not going to do these in Unit 1, because these can get quite complex. So it depends on what aldehyde, what alcohol you mix together, you'll get a varied product. But we're going to cover these when we do carbs. Okay, and this is the mechanism. Okay, the same thing can happen with a ketone. When form a intermediate compound in a final product when we mix the ketone and alcohols together. And there's a way, I have a little technique. How can you tell hemiketal from a ketal, for example? It has to do with, looking for certain combinations of molecules of atoms. Okay, see, this is starting to look like carbohydrates. Okay, and then this is okay, so this is Unit 2. And that's how I'm going to start the carb chapter, is with this here, talking about the the alcohol plus ketone aldehyde. forming these ketals and acetals. Okay. Let's see, okay, something interesting, formaldehyde, of course, is used to embalm animals or humans. That's why it's not particularly good to be around, because it'll start embalming you. Acetone we already talked about. And again, these guys, we have alcohols, we have ketones. Another ketone, another ketone. Have I put up old tests on Canvas yet? Okay. Regarding that previous chat, Caitlin. Aldehydes have one carbon attached to it. And then, well, I guess formaldehyde has two, but most of the time it's got another carbon there.
Oh, no, that was when you were explaining to someone the difference between an aldehyde and a ketone. And I just kind of rewrote what that other slide said in case they missed it. That's kind of verbatim what that first slide said to distinguish them.
Okay,
It wasn't really like a question or anything.
okay. I'm trying to be responsive now. Okay, again, you can see we're starting to get into, we have an ether, alcohol, aldehyde, I mean, another aldehyde, alkene. So these biological molecules have a whole bunch of stuff in them. So when you're, as an organic chemist, when you're trying to make this stuff, you've got to figure out what the precursor is of the thing you're trying to make. And it can get complicated, because if you have lots of functional groups, the chemicals you put in there may affect the other functional groups and not keep them the same. So you've got to devise ways to make them stay stable. And also form cyclic compounds as well. These things can get kind of interesting when you build models of them. So, okay, that's it for aldehydes and ketones.
Did we need to know about the hydrolysis reactions?
You mean with under back up, let's see. This guy here, when you say hydrolysis?
I think right above that, it talks about hydrolysis reactions. I didn't know if you just like went
Oh.
over it, or?
No, not, this is gonna be start of unit 2.
Oh, okay.
You see, this has got the, okay, when you take an alcohol in a ketone aldehyde, you end up making that. To go the opposite way is hydrolysis. So no, we won't deal with that. That'd be unit 2. And you get this in carbs as well. Basically, when you have that glucose, this is a hemiacetal. Okay. This thing can open up. To an aldehyde. So cyclic sugars can open and close. And that's what makes, that's why it's the chemistry of carbohydrates, because carbohydrates are hemiacetals. So this gets real interesting. So again, it's the two. And the reason why I keep this to unit 2 is test 1 includes aldehydes and ketones. So you know those reactions really well. So when I start talking about this one, this really adds a big layer of complication onto aldehydes and ketones. And I just want to have you already studied aldehydes and ketones for test 1 before we get into this. That's why I'm holding off. And, again, this is unit 2. Yeah. Yeah, Wednesday is going to be a lecture review and lab is going to be review as well. So it's going to be kind of a review day. In fact, it's too bad the lab isn't open. So yeah, we're definitely reviewing on Wednesday. I'm probably going to start at 1 rather than noon because the lab is going to be review as well. Now, the review is going to be 90% reactions. That's what most people have trouble with in this class. I've been doing this for decades, this class, and reactions are it. So that's why I'm going to go through a zillion reaction examples. And you need to really get into this. The test on Monday is going to be in lab. So I'm going to have Monday test and a Wednesday test. They're not going to be the same test, obviously. So whatever your lab session is, just go in that day prepared to take that test. It'll be an in-person test on paper. I do want you to stick to your Monday versus Wednesday lab sections. Otherwise, we won't have room in lab. I mean, I wish I had enough. Actually, I wonder if there's a spare room we can go to instead of lab. I might be able to get a lecture room downstairs for Wednesday, and we can all just go to Wednesday. Okay, I'll let you know if that's going on. Yeah, anyway, Wednesday will be a review then. In fact, as of right now, let's start at 1 o'clock on Wednesday for our online, and then I'll see everyone. What reactions? The reactions of alkanes, alkenes, alcohols, thiols, aldehydes, and ketones. I've been going through lots of reactions. Correct, not open notes. What I'm going to give you though is that I will give you this though. I'll give you the one that has the aldehydes and ketones on it. This one. This was my old unit 1 when I had 5 units. So I need to make one that's for the new unit 1, which would include the aldehydes and ketones without the ketals and acetals in it. Any other questions? Now, I really want you to take advantage of Wednesday. There's a lot we've covered. There's a lot of detail that we've covered. That's why in dry lab number 2, I gave you the packet I made up, and I said do the even or odds. If you do one versus the other, you'll have a lot more practice. If you do the odds, then there's all the evens you can do. Lots and lots of practice, plus the additional worksheets I'm putting up. I'm going to put up some aldehyde and ketone worksheets as well. I'm going to do that as soon as we're done here. So, are there any questions other than whatever I answered? Okay, you guys are lucky. I almost didn't make it to lab today. I was feeling very poorly this morning, but I feel fine now. I don't know what was going on, but anyway, I feel good now. All right, so no more questions. I'm going to leave it, and we will. I will see the Monday folks in a little while. Okay, take care, everyone.